Welcome to the Deep Dive. Today we're diving into a paper that's really shaking things up in the world of symbolic regression.
Oh, yeah.
Where algorithms are trying to discover those mathematical formulas hidden within data.
Right.
It's called Improving Genetic Programming for Symbolic Regression with Equality Graphs.
Okay.
And it's really all about making this whole process way more efficient.
Yeah, what's fascinating here is that these symbolic regression algorithms often kind of get bogged down, exploring tons of equations that are essentially the same, just written in slightly different ways.
Interesting.
Like imagine you're trying to find the best route on a map.
Right.
But you keep going in circles, just checking the same paths again and again.
Oh, I see.
So this paper introduces this thing called EGP, which uses this clever thing called an equality graph to help the algorithm recognize when it's going in circles and steer it towards, uncharted territory.
Okay, so it's like giving the algorithm a bird's eye view of the map, so you can see the bigger picture and avoid those redundant paths.
Exactly. And that's super important because these symbolic regression problems can get really hard to solve quickly.
I bet.
They fall into this category called NP hard.
Okay.
Meaning the time it takes to find the best solution just explodes as the problem gets bigger.
Wow.
And on top of that, we often have multiple good solutions.
Yeah.
But finding the absolute best one, the global optimum, it's like finding a needle in a haystack.
So EGP is like giving the algorithm a metal detector to find that needle faster.
That's a great analogy. Now, to understand how EGG works, we need to kind of delve a bit into how these algorithms traditionally represent mathematical expressions.
All right.
They use something called expression trees, which are kind of like family trees.
Okay.
But instead of people, we have mathematical operations like plus, minus, times, divide,
And just like a family tree can have branches representing different family members, an expression tree can have branches representing different parts of a mathematical equation.
Precisely. And the problem is you can have countless trees that all represent the same underlying mathematical concept.
Oh, interesting.
For example, 2 times x can be expressed as x plus x, or even x squared divided by x. They're all equivalent, but traditional algorithms might waste time exploring each of them separately.
And this is where the equality graph comes in, acting as a sort of memory for the algorithm.
Exactly. The equality graph allows EGDRIP to recognize that these seemingly different expressions are actually equivalent. So it doesn't waste time evaluating them repeatedly.
Okay.
This lets the algorithm focus its energy on exploring truly new possibilities, making the whole process much more efficient.
So it's like giving the algorithm a cheat sheet to avoid those repetitive calculations.
Precisely. And this has actually sparked some debate in the field. Because some researchers believe that a bit of redundancy can actually help the algorithm explore different paths to the same solution.
Interesting.
However, this paper makes a really compelling case for the efficiency gains of reducing redundancy with the equality graph.
I'm getting the big picture.
Yeah.
But I'm curious about how EGP actually works on a practical level.
Sure.
Like, how does it use this equality graph to guide the search process?
That's a great question. Let's start with the concept of genetic programming.
Okay.
Which is a common approach to symbolic regression. It's inspired by, biological evolution, where algorithms evolve solutions over time through processes like crossover and mutation.
So it's like survival of the fittest, but for mathematical equations.
Exactly. Now, EGP modifies these evolutionary processes to leverage the equality graph. In crossover, where 2 parent equations are combined to create offspring equations. EGP only allows combinations that will result in a truly new expression, preventing the creation of redundant equations.
So it's like selective breeding for equations, ensuring that each new generation is truly unique and innovative.
That's a fantastic way to put it. And it's a similar story with mutation,
Okay.
where parts of an equation are randomly changed. EGG checks if the mutated equation is truly novel.
Right.
If it isn't, it tweaks the mutation to ensure it leads to something new, preventing the algorithm from getting stuck in a rut.
So EGP is essentially making the algorithm more intelligent and efficient by incorporating this memory of past explorations via the equality graph.
Precisely. It's like giving the algorithm a map that highlights all the areas it has already explored, allowing it to focus its efforts on discovering uncharted territories.
Now, all this sounds very promising in theory, but I'm sure our listeners are eager to know how well this actually works in practice.
Yeah.
Did the authors put EGP to the test?
They absolutely did, and the results are quite impressive.
Do tell.
So they put EGP through really rigorous evaluation, testing it on a variety of benchmark datasets, including some that were specifically designed to really challenge these symbolic regression algorithms, and then also some real-world datasets, from various scientific and engineering fields.
So a good mix to see how well it handles both theoretical and practical problems.
Exactly. And they didn't just test EGP in isolation.
Right.
They actually compared its performance to 3 other symbolic regression algorithms.
Interesting.
So there was like a simple genetic programming algorithm, and then 2 more sophisticated algorithms, Operon and PYSR. Which incorporate some additional techniques to improve performance.
So it's a real head-to-head competition to see where EGP stacks up.
Precisely. And the results, they really speak for themselves. EGP consistently performed as well as or even better than the best competing algorithm on most of the benchmark datasets.
That's impressive.
And this is especially impressive considering EGP is conceptually simpler than those other state-of-the-art algorithms.
It's like David going up against Goliath and holding its own, proving that sometimes a simpler, more focused approach can be just as effective.
That's a great analogy. It really highlights the power of this equality graph to fundamentally improve the efficiency of the search process without relying on, those complex bells and whistles.
Now, I'm curious about how EGG fared on those real-world data sets.
Sure.
After all, those are the problems where it really needs to shine if it's going to make a practical impact.
Well, on those real-world data sets, EGP really showed its potential. It consistently achieved a high ranking, often taking the top spot or coming in, a close second.
So it's not just a theoretical champion. It can handle the messy, complex problems we encounter in the real world.
Right.
That's encouraging.
Absolutely. One of the key metrics they use to evaluate performance is something called AUC, or area under the curve. Think of it as like a measure of reliability, indicating how consistently the algorithm can find a good solution.
So it's not just about getting lucky once in a while, it's about consistently delivering good results.
Exactly. And EGSpeed had high AUC values across the board, so suggesting, it's a reliable workhorse, consistently finding good solutions, even when faced with challenging problems.
So EGP is accurate and reliable, but what about speed?
Right.
I know you mentioned that EGP wasn't always the absolute fastest.
Yeah.
But how did it compare to those more complex algorithms, especially PYSR?
That's a great question. While EGP wasn't always as fast as Operon, which is known for its speed, it consistently outperformed PYSR on most datasets.
Interesting.
Particularly those with, higher dimensions or larger datasets.
So even though it's conceptually simpler, it's not sacrificing speed for simplicity.
Exactly. And remember, the authors didn't even incorporate techniques like multi-threading. Which could, further boost EG's speed.
So there's still room for optimization.
Yeah, definitely.
That's exciting to think about even faster versions of EGP in the future.
Indeed. Now let's talk about something called the hypervolume of the Pareto front. Which might sound a bit technical, but it's actually a pretty intuitive concept.
I'm all ears. Break it down for us.
In symbolic regression, we often want solutions that kind of balance multiple objectives. For example, we might want an equation that's both accurate, but also simple. An equation that's easy to understand and use.
Makes sense. A super complicated equation, even if it's slightly more accurate, might not be as useful in practice.
Precisely. Now imagine plotting all the possible solutions on a graph. The Pareto front represents the solutions where you can't improve one objective without sacrificing the other. It's like finding that sweet spot between accuracy and simplicity.
Gotcha.
The hypervolume is simply a measure of how much area this Pareto front covers. A larger hypervolume basically means that the algorithm has found a more diverse set of good solutions, each offering different trade-offs.
So it's not just about finding a single best solution. It's about finding a range of good options that might be suitable for different situations.
Exactly. And EGP performed admirably in this regard. It consistently achieved a comparable hypervolume to the other state-of-the-art algorithms, especially on those real-world data sets, showing that it's not sacrificing solution diversity for efficiency.
This all sounds very promising.
Yeah.
But no algorithm is perfect.
Right.
I'm sure EGP has some limitations.
Of course. One limitation is that EGP currently relies on a set of predefined rules to determine which expressions are considered equivalent and can be grouped together in the equality graph.
Right.
But sometimes there might be more complex or subtle equivalences that these rules don't capture.
So it's like having a map that doesn't show all the possible paths.
Right.
And the algorithm might miss a shortcut or a hidden route.
That's a great way to put it. It's definitely an area where further research could lead to even more significant performance improvements.
Like imagine if Egg could learn these equivalence rules on the fly, you know, adapting to the specific problem at hand.
Right.
That would be incredible.
It would be a game changer. Another limitation is that as the search progresses and the equality graph grows larger, it can become computationally expensive to manage.
I see.
It's like having a map that becomes so detailed and complex that it just takes a lot of processing power to navigate.
So finding ways to optimize the management of the equality graph is another area for future research.
Absolutely. It's about finding that balance between the richness of information the graph provides and the computational resources required to handle it.
Now, before we move on to our novel notions segment, where we explore some outlandish yet plausible research ideas inspired by this work, I want to touch on something the authors emphasized. They didn't use any large language models, LLMs, in their research. Why is that noteworthy?
That's a great observation. There's a tendency in AI research today to rely very heavily on LLMs for various tasks. And while LLMs are undeniably powerful, this paper is a reminder that sometimes a more focused, well-designed algorithm like EGP can achieve remarkable results without the computational overhead and complexity of LLMs.
It's like choosing the right tool for the job. Sometimes a scalpel is more effective than a sledgehammer.
Precisely. This highlights the importance of continued research into fundamental algorithms and data structures. There's still so much we can achieve with clever algorithms like EGG.
Okay, I'm ready to let my imagination run wild. What novel notions have you come up with based on this work?
Well, one thought that comes to mind is taking this whole idea of the equality graph, you know, beyond just mathematical expressions and applying it to other types of data and algorithms.
Okay, I'm intrigued. How would that work?
Imagine using an equality graph to represent relationships between images.
Interesting.
You could have, you know, different images that are visually distinct, but conceptually similar. Like different photos of a cat.
So the equality graph could help an image recognition algorithm realize that these different images are essentially the same.
Exactly. This could significantly improve the efficiency and accuracy of image recognition systems, especially when dealing with these large and diverse data sets.
Yeah, makes sense.
It's like teaching the algorithm to recognize the underlying concept of cat rather than just memorizing specific pixel patterns.
That's a fascinating idea. It's like extending the concept of equivalence from the mathematical realm to the visual realm.
Precisely. And we could even take it further.
Oh, really?
Imagine applying equality graphs to natural language processing. Where, you know, different words or phrases can convey the same meaning. The algorithm could then learn to group these synonyms or paraphrases together, leading to a more nuanced understanding of language.
That would be incredibly powerful. It would be like teaching a machine to understand those subtle nuances of human language, going beyond just the literal meaning of words.
Exactly. And this could have huge implications for, you know, things like machine translation, text summarization, even chatbot development.
Wow.
Imagine a chatbot that can really understand your intent, even if you express it in different ways.
Now, that's a novel notion I can get behind. It's like we're talking about giving machines this deeper level of understanding, you know, a way to grasp the essence of things rather than just those surface details.
I completely agree. And I think this is just the tip of the iceberg. The concept of these equality graphs has the potential to revolutionize the way we think about and design algorithms across a wide range of fields.
This has been an incredibly thought-provoking deep dive. We've gone from, you know, the nitty-gritty details of symbolic regression to some truly mind-bending possibilities for the future of AI.
It's amazing how a seemingly simple idea like the equality graph can unlock so much potential.
It's a testament to the power of human ingenuity and the ever-evolving landscape of machine learning.
Absolutely.
Well, we hope this deep dive has inspired you to think differently about, those algorithms that shape our world
Definitely.
and the endless possibilities they hold.
Until next time, keep exploring, keep questioning, and keep diving deep into this fascinating world of machine learning.
And remember, sometimes the most elegant solutions are the ones that help us see the world in a new light.